which are above the curve, then you get the supremum of the function. So in that case, you get a UPF, and UPF is equal to capital M into xi minus xi minus 1. So this is just a standard definition of UPF LPF. I'm sure that you must be aware of it, but just to revise, I have just stated the definition. Now, next part is when do we say the function is Riemann integration? So to find out Riemann integration, you need to find out lower integral, which is denoted by LF. And LF is basically the supremum of all LPF, such that the P is any partition of closed interval information. Right? So of course you should we already assume that your function here is bounded function, P is partition. These all are we have to consider. So here when I define LF, it is supremum of LPF such that P is any partition of LF. So which is also written as supremum of LPF, where P written at denominator. So P is any partition of closed interval A comma B, and say and UPF, or maybe here I have written UF, which is called as a upper integral, so which is same as infimum of all UFP or UFP such that P is any partition of closed interval A comma B. So here UFP, I have used the symbol UFP. So so if UF and LF both are same, then we say that the function is R integral. So that in other words, the lower integral is equal to upper integral, LF is equal to UF, then in that case function is called as a Riemann integral. So Riemann was a scientist so who gave the idea of integration. So to honor this, we say R integrable. So if it's said to be R integrable on closed interval A comma B, and the common value, this integral value is called as a UF value, or it is also called as a, or it is LF. Now here is some question which does boundedness imply, if the function is bounded, can I say the function is Riemann integrable? So answer is no. We cannot say boundedness alone does not sufficient to guarantee the Riemann integration. If I say it is no, I should give a counter example. And the counter example, it is a Dirichlet function. So this function is basically f of x is 1 when x is between rational intersection close interval 0 comma 1. That means all the rational points from close interval 0 comma 1. And it is 0 when x is not in rational. So basically x is in irrational. Right. So now here you could see that f is bounded because the upper bound f has maximum value 1 and the minimum value 0. So here the f is bounded between 0 to 1. It is, but it is discontinuous at every point in closed interval 0 comma 1. So this is a function where discontinuous on every point of closed interval 0 comma 1. And further, if you find out LF, here the LF of the function will turn out to be 0. This I keep it as an exercise. You can check out. And UF will turn out to be 1. So UF is not equal to LF, implies that the function is not R integrable. So you start with a arbitrary partition x0, which is equal to 0, x1 dot 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 xn is equal to 1. If you start with this partition, this is an arbitrary partition, you'll get UF is equal to 0 and LF is equal to 1. So the conclusion is F is not Riemann integrable on closed interval 0 comma 1. Okay, so guys, are you with me? I just want to know any response from the student. Hello.
Hello, sir. What are you saying? Please say one.
Yeah. So are you with me? I just wanted to confirm whether I am
Yes, yes, yes,
audible.
sir.
Yeah.
Yes,
Okay.
yes.
Okay. Thank you so much. Thank you so much. Now next question is, can function be unbounded and still remain integrable? So if the function is unbounded, can we say it is R integrable? Answer to this, yes. No, it cannot be. Riemann integrability required boundedness. So it's very necessary condition that function must be bounded. And here is a nice example where the function is unbounded, but it is not Riemann integrable. So fx is equal to 1 by x and defined on the closed interval 0, comma 1. You could observe that the graph of this function over 0 to 1, this function basically as x approaches to 0, the graph of the function uh, goes to basically as x approaches to 0, your f of x will approaches to, that is as x approaches to 0, 1 by x will approach to infinity. So that means the function is not bounded. You cannot find. So it is not bounded on closed interval 0, comma open interval 0, comma 1. So since it is not bounded, you cannot find out the area below the curve. So implies that f is not Riemann integrable on closed interval 0, comma 1. So these two examples basically bounded doesn't imply it is Riemann integrable. That's the example. Counter example was a Dirichlet function, and second one is unbounded also doesn't imply that it is Riemann integrable. The one of the best example is 1 by x is equal to open interval 0, comma 1. As x approaches to 0, 1 by x approaches to infinity. So it is not bounded, hence it is not a Riemann integrable. So you could also observe that this function is continuous. This function is continuous but not bounded. Hence, means maybe we will have a theorem at in the upcoming page where we will say that every continuous function which is bounded is R integrated. Then there is one important theorem. This is called as the necessary and sufficient condition for Riemann integrability, which says that if f is R integrable on closed interval a comma b, if and only if for every epsilon greater than 0, if you could find out at least one partition P of closed interval a comma b such that upper sum minus lower sum is less than epsilon, then if this is happening, if this is true, then we say that the function is Riemann integrable. So many a times people use this theorem to prove that the function is Riemann integrable. Basically, they take a suitable partition and show that the upper sum minus lower sum turn out to be less than epsilon, implies that for every epsilon, then we say that the function is R integrable. Then this is one more result which will help us to check the Riemann integrability. Every monotone function, monotone means it is monotonic increasing or monotonic decreasing, then on a closed interval a comma b is Riemann integrable. So now onwards I'll assume that when I talk about Riemann integrability, when I say the function is Riemann integrable, it is by default bounded. So we cannot have a function bounded. Every function which is Riemann integrable is by default bounded. So here when I say monotone function, by default the boundedness is already there. A bounded and monotone function on closed interval a comma b is Riemann integrable. Then this is algebra of Riemann integrability, which says that if f and g are Riemann integrable on closed interval a comma b, then f plus g, f into g, the modulus of f, these all are the Riemann integrable function. I have not covered one, even the lambda times f is also Riemann integrable, right, where lambda is a scalar. Of course, the converse of this theorem you could take is the converse true. Uh, so that means, for example, if I say f comma g are integrable, this would imply f plus g is R integrable. But the converse is not true. You can. So if the converse is not true, one should give a counter example. So here is a counter example. Fx is equal to, you can take it as 1 comma 0, where of course my domain is closed interval 0 comma 1, I'm assuming. So where x belongs to all the rational from the closed interval 0 comma 1. that's basically Dirichlet function. X belongs to all the irrational uh, intersection with close interval 0 comma 1, and you take gx is basically, or maybe gx, just swap the uh, values. So here 0 1, and here x is belongs to close interval 0 comma 1 intersection with rational, and here x belongs to uh, close interval 0 comma 1 intersection with irrational. And if you find out f plus g here, so f plus g will turn out to be 1, which is a constant function, and here I have not mentioned. Constant functions are also Riemann integrable. So f plus g is Riemann integrable. However, f and g are not R integrable. So the converse of this theorem is not true. Now I'll leave it on you that you also check f plus g mod f and lambda f, these three. If they are R integrable, can I say that f and g are R integrable? Can I say that if mod f is R integrable, f is R integrable? Similarly, if the lambda f is R integrable, can I say that f is R integrable? That could be a good exercise. You can check out this. So a bounded function on closed interval a comma b is Riemann integrable if and only, sorry. So if it has finitely many discontinuities. Here I must have stated the yeah, every continuous function on a closed interval a comma b is Riemann integrable. So a function which is defined on a closed interval is basically bounded. Continuous function defined on closed interval a comma b is bounded. So this is going to be a bounded function. So it is going to be R integrable. So continuous function defined on closed interval. This is very important theorem. Every continuous function defined on a closed interval a comma b is Riemann integrable. And then last one, a bounded function defined on closed interval a comma b is Riemann integrable if it has finitely many discontinuities. So this means that a function which has finitely many discontinuity is also going to be R integrable. And a function which has infinitely many discontinuities, which are uncountable discontinuities, that is not going to be R integrable. And an example is a Dirichlet function we have seen, which has uncountable discontinuities, so hence it is not R integrable. And then this is a Riemann sum definition. So if f is a real valued function, so Sn is defined as fxi star. Uh, this delta x stands for basically uh, xi minus 1. And this, where does xi star belongs? It is basically belongs to a point from any point from xi minus 1 to xi. And this is very important. This says that if you find out limit as n goes to infinity of Riemann sum, then you get basically Riemann integration. The Riemann sum approximate the area under the curve fx over the closed interval a comma b as n goes to infinity. The Riemann sum approaches the definite integral. And then these are the theorems which will assume that the algebra of integral, if f is R integrable, then yeah, algebra, we have seen this already. Then additive property. So you can definitely insert a point A to C, C to B. If f is Riemann integrable over A to B, then, and if C is a point between A to B, then it is Riemann integrable from A to C and C to B. Then order preservance, if f is less than equal to g, then the integral is also less than equal to, also preserves this. And then this mean value theorem for integral. If f is continuous on closed interval a comma b, then there exists c belongs to closed interval a comma b, such that integral a to b f of x dx is equal to f of c uh, times b minus a. Well, this all are the standard result. You might be aware of this. Even function, if the function is even, then integral from minus a to a f of x is equal to 2 times this integral. This small trick may help you for the lengthy calculation. What is even and odd function? So if f of minus x is equal to f of x, then we say it is even function. And if f of minus x is equal to minus of f of x, then we say it as an odd function. And then this is substitution rule, which says that if f is equal to u times pi of x, yeah, I'll share these notes. I'm sure that you will go through this. Now I have, based on this theory, I have just framed the some MCQs question. So Let's try to answer those MCQ questions. Okay, so I'll read out this question, and I'll be happy if this MCQ's pattern will goes on a interactive way. So I have a function fx. This is basically a Dirichlet function. Then you have to answer f is whether it is continuous, whether it is Riemann integrable, whether it is bounded but not Riemann integrable, and it is unbounded. So you have to tell me which option is correct, justify that option, and if possible, why the other options are not correct. That also you can justify. So I'll wait for some time if somebody can answer me. So this is basically a Dirichlet function. Okay, so let me ask you the question: is this a bounded function? Is f bounded? What is your guess? Yes, guys. Is f bounded? When do we say a function is bounded? Is function bounded?
Yes, sir.
Yeah, it is bounded. Yes. What is upper bound for this function? When do we say a function is bounded? Rishma, good, very good. When do we say function is bounded? When f is bounded. Okay, so Reshma is saying that it is bounded. Yes. So let's justify this why it is bounded. Reshma, was it a guess or with some justification you said it is bounded or any? Yes, Reshma.
Sir, upper bound 1 and lower bound 0, sir.
Very good. So it fx, you could see that fx lies between 0 to 1. So for every x belongs to closed interval 0 comma 1. So this means it has upper bound as well as lower bound. So clearly f is bounded function. Now, is this a continuous function? So in fact, this function has at every point of the domain, it is discontinuous. And you might have seen maybe at beginning only, I have shared this function. Yeah, if you could remember, there is a discontinuous at every point. And here LF is not equal to UF because if you find out LF is turn out to be 0 and UF to be 1. So the conclusion is F is not bounded, though it is bounded. So, so, so which is the option here? So it is not continuous, so the first option will not come. Then it is bounded, that's very true. Unbounded will also not come. So now Riemann integrable or not, and we have seen in the Dirichlet function is not Riemann integrable. So the option is correct, option is C. So let me tell you this, even if I have fx is equal to sum here, instead of 1, I may take it as -1 and x belongs to rational intersection with 0 comma 1. X belongs to irrational intersection. Still it is not R integrable because this is still a Dirichlet function. So here you may have 1, 0, 1 may take any two different value. At last you will get function is not R integrable straight away, and hence it is No, so UF is not equal to LF, hence it is not R integrable. Okay, so here is the answer also. Bounded but not in your R integrable. The Dirichlet function is bounded but discontinuous at every point in the closed interval 0, comma 1, and LF is not equal to UF. So hence it is not Riemann integrable. Then the second question, uh, f of x is equal to x square on closed interval 0, comma 1. Then you have to answer whether f is not bounded, f is not R integrable, f is Riemann integrable and continuous, and f is discontinuous. So maybe let me ask you the question, uh, have you studied this topic before, Riemann integration, or this is first time? So I am
Has
not aware
had
that
has studied before during
before.
semesters.
So you have some ideas about this Riemann
Yeah, yeah.
integration.
Hmm.
And maybe starting I have tried my level best to complete some prerequisites. I know that it is on very fast mode, but since time is a constraint, so I have just considering that I have just gone through some prerequisites. So let's use those prerequisites and try to answer this. So if I have a fx is equal to x square defined on closed interval 0, comma 1, then the first question is whether f is not bounded, f is not R integrable, f is integrable and continuous, f is discontinuous. So what can you say about continuity of this? Is this a continuous function? F of
Yes,
x
sir,
is
it
equal to
Yes,
is.
x
yes.
square. Yeah, it is continuous because it's a polynomial, and being a polynomial, it is continuous. Now, is it a bounded function?
Yes, sir.
Yeah, is f bounded? Yes. So what is you could see that on closed interval 0, comma 1. You can see that the 1 is the upper bound, 0 is the lower bound here. So it is bounded also. So a continuous function which is bound, a function which is a continuous function which is defined on closed interval is always R integrable. So you could see that which option will turn here, correct?
Option C.
Options.
Option C. Because f is Riemann integrable and it is continuous also.
Sir, we can also say that the point of discontinuity is phi, and which is countable, so it is Riemann
Yeah,
integrable.
that is also fine. That is basically I thought to take that major zero concept here, but then I thought whether at undergraduate level whether everybody is aware of this or not. So that also a very clever approach. The countably many discontinuities, so you can it's zero, hence it is Riemann integral. That's correct, absolutely correct. So if you are aware of this Pager zero concept, you can definitely go with that interpretation and you get your answer. Very good. Good. So if f is Riemann integrable and continuous, as f of x is equal to x square, is continuous and bounded on closed interval 0, comma 1. So it is Riemann integrable. It's a standard theorem basically. Then here is the third question. So if f of x is equal to 1 by x, defined on open interval 0, comma 1, then what can you say about this function? So the option is f is bounded and integrable, f is unbounded and not Riemann integrable, f is continuous and integrable, f is bounded and discontinuous. So you need to check first boundedness. Is function bounded?
No, sir.
Yeah, it's not bounded because as x approaches to 0, your f of x will approach to infinity. So function is not bounded straight away and not bounded. You only have one option, yeah, in all the three. So f is not bounded, so then straight away can say that it is not R integrable because boundedness is a necessary condition to check the Riemann integrability. So since it is not bounded, it is not going to be R integrable. So the correct option is B. So f is unbounded and not Riemann integrable. So fx is unbounded near x is equal to 0. So it fails the boundedness condition for Riemann integrable. Then there is a question number 4. Yeah. So this is basically a standard theorem. You just have to tell me which options is correct. If f is Riemann integrable on closed interval a comma b, then for every epsilon greater than 0, there exists a partition. That's very important. Existence of partition itself, such that pictures, this is basically Riemann criteria I have written.
So option B.
Yeah. So upper sum minus lower sum must be less than epsilon. Very good. It's a Riemann criteria. So this is Riemann criteria in terms of upper sum and lower sum. The difference can be made arbitrarily small for integrable function. Now here is fx is equal to x, if x is not equal to 1 and it is 5, then you have to see that defined on the closed interval 0 comma 2, then you have to check whether f is Riemann integrable or not. Yeah, so f is bounded, f is not Riemann integrable, f is Riemann integrable, f is discontinuous.
So option D.
Option D says that f is discontinuous at everywhere. Okay. So why you are saying that it is discontinuous at everywhere? So let us check the discontinuity at one point first. So which is which point you would like to check the continuity? Let us check the continuity. So which point you would like to check the continuity of a fx? Now x not equal to 1, x is equal to 1. So which point?
So 8.1.
Yeah, very good. So let us check the continuity of f at x is equal to 1. So when do we say a function is continuous? So we have many definitions, or maybe you can use epsilon delta approach, or you can use the left hand limit, right hand limit, and you find out what is whether limit exists or not. If the limit exists and if it turn out to be f at that point, then we say that it is continuous. So let's check. So let's find out limit as x approaches to 1, f of x. If this limit exists, say L, and if L is also equal to f of 1, then we can definitely say at x is equal to 1. Okay. This is how we are going to check the continuity. So if limit of x goes to 1, f of x exists, say L, and if L is equal to f at 1, then we say that f is continuous. So whether limit exists or not, how do we check? We basically check out left hand limit and right hand limit. So if left hand limit is same as right hand limit, then we say that function has a limit. So limit as x approaches to 1 from positive side. What is fx?
So it is 1.
Yeah, so limit as x approaches to 1 positive. So it is x only. So it is 1. And what is limit as x approaches to from negative side?
It is also 1.
Yeah, it is also 1. 1 from negative side, fx. This is basically limit x approaches to 1. From negative side, it is x. And this is again 1. So left hand limit and right hand limit. So this is L, H, L. So limit, left hand limit and right hand limit are same. So if left hand limit and right hand limit are same, this would imply limit exists. F of x exists. And what is limiting value? इसका limiting value क्या होगा? ये जो
5.
limit value होगा, that will be value will be 1. Now we have to check the L value is here 1. Now we have to check that whether L is equal to f at 1. Now what is, so here L is 1. And what is f at 1 here?
5.
What is f at 1? Yeah, it is 5. f at 1 is 5. So you could see that L is not equal to f at 1. So though the limit exists, but the limiting value is not equal to f at 1. So the function has a limit, but it is not continuous. So the ultimate conclusion is f is not continuous at x is equal to 1. Now, maybe I don't know your name, but you said option D, discontinuous are everywhere. I'll just suggest if you take any point which is not 1, then you will always end up with the left hand limit, right hand limit as x, which is that particular value, and which is equal to that f at that p on, again. So at every point it is continuous, but at x is equal to 1 only it has a problem. So the function is continuous. What is my conclusion is f is discontinuous at x is equal to 1, and at other points of closed interval 0 comma 1, 0 comma 2, it is continuous. Apart from x is equal to 1, it is continuous everywhere except at x is equal to 1, it has a problem. So number of discontinuities is countable, and we have result, we have already stated a result which says that here I'll show that result. It says that if a bounded function is R integrable if it had finitely many discontinuities. So now here you could see that the function has finitely many discontinuities. That is only one point it is kind of discontinuous. So it has continuous. So what is the integration of this now? Maybe f is not continuous at x is equal to, so f is discontinuous. So this would imply uh, discontinuities are finitely many. And if discontinuities are finitely many, it is going to be R integrable. So the function, though it is discontinuous, but it is R integrable. So the option 1 will not come because this function defined on the closed interval, you can definitely find out the bound for this. So 5 is the upper bound and 0 is the lower bound. So this is bounded. Not bounded will not come because it is bounded. F is not R integrable will not come because we have just shown that F is R integrable. So option to this, so F is R integrable. Now my next question is, if it is arc integrable, then you should be in the position to find out the integral value of this. So what is integral value of this? So now integral from 0 to 2, what is fx? Now you may say that here x not equal to 1, x is equal to 1. So I'll just add one point here. If you delete a countably many points from the function, or maybe a single point, a area below the point, the area below, there is no area below the points. So even if you delete this point from the integration, it will not affect on the integral value. Further, in fact, I wanted to add here, even if you delete the countably many points, then also it will not affect on the integral value. So if the integral value of this is 0 to 2, I'll straight away take x because this 5 will not contribute anything. So it is x squared by 2, which will be 4 by 2. So the answer is 2. Right? So the integral value. This is not asked in the exam in this question, but this is just an extension of this. What is integral of this? So maybe answer is f is Riemann integrable. The function is bounded and discontinuous only at one point. That is finitely many discontinuities. Hence it is R integrable. Now here is a question. If I have fx is equal to 0, 1 and 0, your question is to find out, and Pn is a uniform partition. So what is uniform partition? So your Pn is basically 0, 1 by n, 2 by n, dot, dot, dot. n by n, which is equal to 1, is the partition. Then you have to find out UFPN and LFPN. You find out that and then take a limit. So what will be the UFPN? We know that UFPN is basically summation I goes from 1 to n, capital Mi, yeah, xi minus xi minus. So what will be the capital Mi here? So between any two rationals, if you take any 2 points, so density theorem says that you will have infinitely many rational and infinitely many irrational. So you will have always capital Mi will be always 1, and here xi will be I upon n minus I minus 1 upon n, and which will turn out to be I goes from 1 to n. So 1 by n will be outside. If you take difference of this, you'll have the 1 only. So it is basically 1 by n summation I goes from 1 to n 1. So 1 added n times. So 1 by n, this is basically 1 plus 1 plus 1 added n times, and n1 added n times. So this is basically 1 by n into 1 into n. So nn will get cancelled. So you're left with 1. So UFPN will be 1. And if you find out limit of UFPN, then limit of UFPN will be 1 only as n goes to infinity. And regarding LFPN, you could see that 0 between any two rational, there are infinitely many rational as well as irrational. So you will always have lower bound as a 0. So in all the cases, your small mi is 0 always. So 0 into anything is always 0, and 0 added n times will give you 0. So LFPN is always 0. So LFPN is always 0. Here it is always 0. But UFPN is 1, so limit is 1. So your correct option is A. Maybe. I think, yeah, A. So I have given a small explanation here. In every subinterval, both rational and irrational number exist. So the supremum is 1 and the infimum is 0 in each subinterval. Hence, you can get it. That is not a difficult part. Okay, now next question. Fx is equal to 1 if x between uh, is not half. Basically, this is equivalent to saying that x is not half, and 0 if x is equal to half. Now, can you tell me what is it? What is whether this is Riemann integrable or not? Or I will ask whether this is continuous or discontinuous. If it is continuous, you have to justify why it is continuous. And if it is discontinuous, you have to give me the point at which it is discontinuous.
Sir, it is discontinuous at point half.
Very good. It is discontinuous at half because limit as x approaches to half from positive side, you will get 1. From negative side also, you will get 1. But f at half is basically 0. So though the limit exists, but it is not equal to f at p. So it is discontinuous at half. And the rest of the point, apart from half, if you take any point from the close interval 0, 1, it is going to be continuous. So the discontinuous are finitely many, or it is countably many. So it implies that f is going to be R integrable. So f is not R integrable, ये नहीं आएगा. F is R integrable. This B and C, there is a clash between B and C. Now we have to find out the integral value, which is the correct answer. So D तो आएगा ही नहीं, A भी नहीं आएगा. What is integral value of 0 to 1 f of x? Now here you could see that when x is equal to half, it is 0. So even if you delete this point, even if you do not ignore this point in the integration, it will not contribute anything in the integration because the area below the point is 0. So the 0 to 1, you can straight away take the function 1 only, and 1 का integration होता है x, where 0 to 1, and I think the answer is 1 minus 0. So B is the correct answer. The f is Riemann integrable, and integral 0 to 1 f of x is equal to 1. Let's see that. Yeah, it's correct. The function is discontinuous only at point which is a major zero set. Okay, I should. Maybe you can say that discontinuities are finitely many. So countable set hai, discontinuity has a major zero set and then value of, you may ignore this. I don't know how many of you are aware of this, but then you can see that the discontinuities are countably many, hence it is Riemann integral. And the value of at a single point does not affect in the integral. So the integral is the same as a constant function 1 over which is 1. Okay. Then here fx is equal to x if x belongs to. Now you could see that. Uh, can you can you identify what is the what which answer will be correct here? Option.
Sir, can we go one by one, as we can clearly see that it is discontinuous at point 1.
Okay. And is this a
So
bounded? Is the function bounded?
yes, sir.
It is bounded also. So a function which is bounded and discontinuous at finitely many points implies that it is R integrable. So this is a standard result we have stated. So it is going to be R integrable. That's very clear. Now the next question is, what is integral value of this? What is integral value of 0 to 1 fx? Yeah. So now, as you said, we go one by one. So f is not R integrable will not come because we have seen that function has countably many discontinuities and bounded. So it is going to be R integrable. So first option will not come. Now there is a confusion between B and C. Both says that it is R integrable, but D is also not correct because it is unbounded. So B and C there is a we have to clarify which is the correct because both says it is R integrable. Only the integral value difference. So let's find out integral value of this. So what is integral value of this? 0 to 1. What fx I should take here? So as I already told you that even a deleting single point does not affect on the integral value. So you can straight away take it is only x. And what is integration of x? It is x square by 2, 0 to 1. So it is 1 by 2. So do I have, which option is correct now?
It's B.
So the Riemann integrable, the function is just continuous. Okay, that's the explanation you can read out. So, okay. So if I have a function of this type, fx is equal to x square, defined on closed interval 0, comma, consider the right hand. So Riemann sum, you can see that. This is Riemann sum of fx because we have taken a partition. Uh, uh, what is a partition here? P is basically 0, 1 by n, 2 by n, 3 by n, blah, 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 and by n. Right? So Riemann sum basically as fp will be basically summation I goes from 1 to f xi star into xi minus xi minus xi minus xi. Right. So this is basically now, so xi star, what is, where does xi star belongs? The xi star basically belongs to xi minus 1 comma xi. So now where I said right endpoint, so I have taken xi star is equal to xi only. So here f at xi, and now what is xi? Xi is basically I by n minus I minus 1 by n. Now what is fxi? fxi is basically x square. So I by n, it is I by n. So it is I by n whole square. And this difference is basically 1 by. So this is Riemann sum, which we call it as Rn. So the question is, what is the limit of Riemann sum? Now, if you remember, we have already done one small, when I define Riemann sum, let me go at the point where I had discussed the Riemann sum. Yeah, we have defined, if you take limit as n goes to infinity of this Sn, then you get basically integral value. So now here I will do the same. So to find out this limit, basically limit as n goes to infinity of Riemann sum, which we denote it as Rn, is basically your integral value 0 to 1 x square. And now this limit is very easy to calculate. This limit is basically, what is it? This
One,
integration, instead of
one by
evaluating
three.
this integration, what is it?
1 by 3.
1 by. So it is x cubed by 3 over 0 to 1. So answer is 1 by. This is option is B. Yeah. So the Riemann sum approximation on this, the limit is. Which of the following is true about the step function? Every step function is discontinuous everywhere. This is not true. I'm sure that you must be knowing what is step functions. It is basically, for example, this function, which is discontinuous only at integer point, right? Similarly,
Sir,
so
uh,
yeah,
sir, a
basically
step
f of x
function,
is
sir, a step
this
function
box
and
function.
pointwise continuous function are same or different?
Sorry,
Sir, step function and pointwise continuous function are similar or different?
they are different. What is the definition of step function? So f of x is equal to greatest integer function. So box x is greatest. Right. So for example, if I wanted to define f of x is equal to box x, x between close interval 0 comma 5, then how do I define this function? This function says that fx is equal to 0 if x is between 0 to strictly less than 1. Now it is 1 if x is between 1 to strictly less than 2. Now it is 2 if x is between 2 to less than 3. So I'll just reduce my domain here. Instead of saying 5, I'll just write it as 3. And now you can see that and it is 3 at x is equal to 3. Now if I draw the graph of this 0, 1, 2 and 3. Now you could see that between 0 to 1 the function is 0. So between 0 to 1 it is 0, but 1 is not included, so it has a discontinuity at 1. So at 1 it will, from 1 to 2 it will take the value 1 only. So suppose this is 1. So from 1 to 2 it is taking value 2, but at 2 is not included, so it will take a jump at 2. So at when from 2 to 3 it is value is 2. So it is 2 to 3. But at 3 it will take a jump. So at 3 it is 3. So this is 3. Right. So you could see that this function has a discontinuity from graph only. So discontinuous at 1, 2 and 3. So discontinuities are finitely many. Hence it is going to be R integrable. So this is question, which is the following is true for the step function. So every step function is discontinuous everywhere is not correct, because it has discontinuity only at the this interval ka jo end point hai, there it will take the jump. So step functions are not Riemann integrable. Well, here the step functions here it is 3. Now we if I do it with interval 0 to 5, then the 4 and 5 will also come. So the discontinuities are finitely many, so they are countably many. And the step functions, this is bounded also. So a function which is has countably many discontinuities and bounded is going to be R integrable. So step functions are R integrable. So the option B is not correct. It says that it is not R integrable, whereas we have seen that it is R integrable. And the step functions are unbounded is also not correct, because it is always bounded. So step functions are Riemann integrable always. Now here the interesting question is, what is integral of this? Now you could see that this here will not have any rectangle. So the area below this line is 0 basically. So 0 to 3, my fx integral value is 0. Plus now from 1 to 2, you could see that if I form the rectangle, then it will give a perfect area, and that area will be 1 only. Base is 1, height is 1. From 2 to 3, if I form a rectangle, you could see that the height is 2 and the base is 1, so 2 into 1. And at 3, there is only point, so there will not be any contribution. So basically it is 3. So the integral value is 3. I would like to take one small question here, which is really one of the interesting question. So if I define fx as a box x, and I say that x belongs to 0 to 100, then it is very clear that the function is Riemann integrable, because it has discontinuity at 1, 2, 3, 4, 5 up to 100. So it has 100 discontinuities, but those discontinuities are countably many. So this is going to be R integrable, because it is bounded also. And if you draw a graph of this, you will have 100 steps basically, up to 100. Now the question is, what is the integration of this? Integration of boxes. Now you could see that for here, for this we could see that 0, 1 and 2. So can you guess what will be the integration of this?
Sir, up to 1 to 99.
Very good. 0, 1, dot, 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 99. And this sum can be easily find out, n into n plus 1 divided by 2. So 99 into 100 divided by 2, that you can answer, right? So maybe I have taken a small number, but in competition, maybe in the exam, sometimes people give you some 5,000 number and then find out the integral. So it means that you have to just add 1 to 4,090 and 9,999 number. That's it. Okay. This is the mean value theorem, which says that then by mean value theorem, the integral value exists. Yeah. So you can find out the integral of this. It is basically x cubed by 3, and it is 2 to 0 f of c into 2, and this is 8 by 3, which is equal to 2 times f of 2, and this would imply f of 2 is equal to 2 will go denominator, so 8 by 3, that is 4 by 3. Okay. And then, okay, so this is a standard mean value theorem. F be a continuous function, non-negative, integrable. Then first mean value theorem integral says that. So option C is correct, because it's a standard theorem. This is a statement of first mean value theorem for integral. Right. Okay, so maybe here I'll stop.
If you have any comments or feedback, you are now free to give your comments.
Thank you so much, sir. It was wonderful, exploring these concepts with you, and I learned so many new things because these topics I have already learned, sir. But the newer things, which are very interested, were very well explained by you, sir. Thank you so much, sir.
Yeah, thank you. Thank you.
Okay, so on behalf of Department of Mathematics, Wilson College, Mumbai, I extend our sincere gratitude to Lieutenant Prakash Sansare, sir, for delivering 4 insightful sessions on functions of one variable as a part of our IIT Jam lecture series. So your clear explanations and systematic approach have greatly enhanced our students' understanding of the subject. We truly appreciate the time, effort, and dedication you have devoted to this initiative. Thank you once again, sir, for your valuable contribution and also for highlighting career opportunities in mathematics. Dear participants, we request your feedback for sir's session. The link for the same is posted in the chat box and will also be posted in Telegram. Thank you.
Thank you, sir.
Yeah, thank you. Thank you so much.